Okay, good. So just a minute. I am sharing my screen. So my presentation is visible to everyone?
Yes, sir.
Okay, good. So once again, good evening to all of you. So today we have second class and name of the subject that is a modeling and control of electric drives. Okay, and we are discussing unit number first. So that is an introduction to electric drives. So now slide number two. So in the previous class, we discussed about the syllabus and course evolution scheme and just fundamental of the electric machines and drives. And also we discussed what we studied in the first semester. Okay. So now we can start our official syllabus. Okay, unit number one. So starting with the block diagram of electric drives. Okay, so just revise the concept one by one component, and each component we will discuss. Then classification of electric drives, then concept and elements of electric drives, and finally we will discuss the torque speed characteristic curve. Okay, otherwise we can see the torque speed characteristic of electrical drives. So these four topic we will discuss in the today's class. Okay, yeah. So my slide is visible to everyone, correct? And current slide is a slide number 4, correct? Yes, student, please confirm this thing.
Yes, sir, it's visual.
Okay. Okay. Yes. So in the first semester, we already discussed the block diagram of electrical drives. Also, in the previous class, we discussed the overview of the block diagram. Okay. So again, I am repeating this thing because this is the most important thing. Okay, so this is the most important thing. So starting with, we can say the power source. Whenever we can say the power source, so that is maybe the AC or maybe the DC. Okay, so alternating current, otherwise the direct current. Okay, and from the power source, we can say we have a converter. So converter is nothing but power electronics converter. Okay, and that is a heart of the drives. Okay, we can say the power electronics, that is a heart of the drives. Okay, and this power electronics converter, what they can do, so they can control the voltage. Okay, so they can control the voltage, otherwise we can say the current, and that voltage and controllable voltage and current, that is directly fed to the machine. Okay, and machine maybe that is your motor, yeah, maybe the generator, yeah, maybe the AC and DC motor. Okay, and this motor, yeah, machine, that is connected with our load. Okay, and that is a mechanical load. Okay, and we all of you know the mechanical load, correct? So whenever we can say the mechanical load, so there is a motion, correct? So we can say the speed. And here is coupling, that is a mechanical transmission shaft, we can say mechanical transmission shaft, correct? And whenever we can say drives, so drives means we have to control the speed, otherwise we have to control the torque of the this mechanical load. Okay, so we have to control the torque, otherwise speed. Okay, whenever we can say we have to control the torque and load, control the torque and speed, it means we have to sense the feedback signal, correct? So this is your feedback, so we can say the sensor signal. Okay, this sensor signal we can give to our controller. Okay, and this controller, maybe the microcontroller, maybe the FPGA, any controller we can use, correct? So nowadays people use the FPGA, that is a field programmable gate array. Okay, so most of the company nowadays using FPGA to design the drive. Okay, and why FPGA? Because of the high clock frequency. Okay, so this is a controller part, and input of controller, that is a your torque, otherwise the speed, that is the input of your controller part, correct? So we can say the controller engine. Okay, and this controller output is going to converter. Okay, to generate the PWM pulses. Okay, and this is, you can see, the closed loop system of your electric drives. Okay, and ultimately, yes, we have to control the electric drive. So this is your finally computer system. Otherwise, we can say the personal system, personal computer. Okay, we can say PC, desktop. So ultimately, this is nothing but your communication link. Okay, so you can easily operate the controller. So this is a simple and most important block diagram of electric drives. Any confusion, student, for this diagram? So this is a fundamental block diagram of electrical drives. Okay, so we should understood very well. Then we can go ahead. Any confusion, student? Any query for this block diagram? I hope no query
No,
because
sir. Let's proceed.
because we already discussed this in the first semester and also in the previous class we discussed. Okay, so now I want the answer from you. So why we are discussing electrical drives? Otherwise, we can say what are the advantages of electrical drives? Any idea? Any idea what are the advantages of the electrical drives? Yes, student. Any idea? What are the advantages of the electrical drives? Yes, Ashish.
Smooth speed
Ashish is
can
there.
may be achieved, sir.
Yeah, Ashish. Ashish, are you there? Yeah, your voice is not coming. Okay. Alok Yadav.
Yes, sir.
Yeah.
Electric drives we can use in like various industrial purposes also, and for elevator system, and for the where we require control of the speed and torque
Mm-hmm.
accurately.
Okay. Yes. Good. Very good. And
Yes.
Amrit Giri, any other additional out advantage you would like to add apart from the Alok Yadav advantages?
Yes, sir. I think the controlling of the speed and torque of the various applications, industrial electric machine applications.
Okay. Okay.
That is.
Okay, good. So we can say we have a many advantages of the electrical drives. Okay, so we can say first advantage, very large range, torque, and speed and torque, power. Correct. So whenever we can say the electric drives, then we can say we have a very large range of torque. So torque, maybe we can say the Newton meter, millinewton meter to kilo Newton meter, very high range, correct? And we can say the speed also, there is a very high range. We can say the power kilowatt to milliwatt to megawatt to gigawatt. Okay, so there is a first advantage, and there is a biggest advantage of electric drives. Free from pollution, that is a second of advantages. Third advantage, it can operate on all four quadrant speed torque plane slide side. So what are the name of the four quadrant? Any one student? Any idea? We can say the four quadrant operation. So what is the meaning of four quadrant? Any idea? So we can say this is maybe this is your speed and this is your torque. Any idea? Four quadrant, maybe this unit is a Newton into meter and this is RPM. So what is the meaning of four quadrant operation? Any idea? Yes, Madhusudan, any idea? What is the meaning of four quadrants?
I think, sir, direction of the load, low torque and speed, mechanical speed is given.
Direction. Okay, we can say the direction. Okay, direction of the speed. Okay. Any other answer?
Forward braking and forward motoring and reverse braking, sir.
Forward braking, reverse
Forward
braking,
motoring
forward
uh,
motoring,
and reverse braking.
reverse braking, forward braking, reverse braking, forward motoring, and reverse motoring. Correct?
Yes, sir.
forward braking, reverse braking, forward motoring, and reverse motoring, correct? Yeah, so we can say we have a 4 operation: forward motoring. So we can say the forward motoring, forward braking, reverse motoring, and reverse braking. So we have a 4 type of 4 coordinate operation of the drives, and that is a possible in the drives operation. And this 4 coordinate is important for the all the application. Okay, maybe we can say the electric vehicle, maybe we can say the crane, otherwise we can say the lift. Any application we mostly operate in the 4 coordinate operation. Correct. We will discuss detail about the 4 quadrant. Fourth application, working independent of the environment condition. Okay, so we can operate our drives independent to the environment condition, correct? And fifth one, the efficiency of the drives is high. Yes, we can say our efficiency is very high, and that efficiency is depend on your power electronics converter. No starting problem, easily start, so not required any refueling, correct? So we can easily start our drives. Okay, so these are the most important advantages of the electrical drives. Now, what about the disadvantages? We know there is not any kind of system that is 100% correct. Suppose we have some advantages, then again we have some disadvantages. So, any idea what type of disadvantages we have in the electrical drives? Yes. Yes, Archana, any idea? So we have a total 4 to 5 advantages. So what about the disadvantages? Is there any disadvantages of electric drives?
I think cost is high.
Correct. So cost is very high. Any other disadvantages?
Uh, I think also
Output is? Okay. So output is what?
output power is also low, I think.
Output power is low. So we can increase the output power by the power electronics converter. So that's why we are saying
Yeah.
efficiency is very high. Suppose
Yes.
output power is low, then efficiency is also low, correct? So we can increase the
Yes.
efficiency by the power electronics converter. That is possible.
Okay.
So major disadvantage is your price. Starting price is very
Yeah.
high. Okay.
Yes.
So there is one of the major disadvantage of electric drives. And second disadvantage, we can say it is a disadvantage, but not the 100% disadvantage. That is a dynamic operation. So we can operate the our drives in the dynamic operation, but sometimes it is not possible to operate the dynamic range. Correct. So these are the few disadvantage of the our electric drives. Okay. Correct. So these are the just fundamental of the electric drive. So we already discussed the block diagram of electric drives, then advantages and disadvantages. Now we can see the classification of the electric drives. Okay, so how we can classify the electric drives? Okay, so first classification, that is a adjustability of the speed. Okay, how we can adjust our speed? So we can say fixed, variable, and servo. Depend on the drive's speed, we can classify our electric drives. So we can classify the electric drive based on the speed parameter. So we can say the speed, fixed speed, variable speed, and servo speed. Okay, so depend on the speed, we can classify the electric drives in 3 category. There is a fixed, variable, and servo. Okay, so we can set the fixed speed drives, variable speed drives, and servo drives. So mostly servo drive, there is a positioning speed, otherwise positioning system. Okay, so there is a first classification. Second classification, motor type and drive controller. Okay, what type of motor we can use in our electric drives? Okay, there is a second classification. So we already know in the universe we can say we have only 2 type of motors, otherwise machine. That is a DC, and second one is AC drives. Okay, so there is a second classification. Third classification, motor power range. Okay, so what is the power range of your motor? So that is we can see the small power range, medium power range, large, and very large. How we can say very large? That is suppose your power rating is in the gigawatt. Okay, suppose that is a gigawatt, then we can say the large operation, very large. So large, that is a megawatt, medium, that is your kilowatt, and small, that is your watt. Okay, so depend on the power rating, we can also classify our drives. And finally, motor rated data. Okay, so there is a fourth one, that is a motor rated data. Okay, and there is a controller rated data, and fifth one, that is a controller rated data. So motor rated data means that is a which type of frame we can use, which type of standard we can use to design this motor. Okay, and what are the temperature level. Okay, so this type of motor data we can take, and then we can classify. Okay, and controller rated data means what type of controller we can use, maybe the FPGA, maybe the microcontroller, maybe the any other controller. Okay, so depend on the this function, we can classify our electric drives. So first one, that is a adjustability of the speed. So depend on the speed, we can classify. Second one, that is a motor type and drive controller, which type of motor we can use, that is AC or DC. Third one, that is a motor power. Fourth one, that is a motor rated data, and fifth one, that is a controller data. So majority we can say we can classify our electric drives in 5 category. Okay, is there any confusion in this slide? Yes, student, any confusion? Okay. Now we can start the elements of the electric drives. Okay, so we use the many elements in the electrical drives. So before going to start the detailed analysis, otherwise detailed modeling of electric drives, first we have to understand the concept and major elements of the electrical drives. Okay, so first one is a power source. Okay, so alternative, otherwise the direct. Okay, so depend on the power frequency, that is a 50 hertz and 60 hertz across the globe. Okay, and direct current, that is maybe the battery, fuel cell, otherwise solar cell. So power source, all of you know. Okay, so that is a depend on power source, we can classify also our techniques, our not techniques, our drives. Okay, and that is a AC, otherwise the DC. Okay, first element. Second element, that is a power processing unit, and that is a nothing but your converter part. Okay, power processing unit, that is a nothing but your converter part, because we have to convert the power from one level to another level, from one source to another source. Okay, so why power processing unit? Because convert the fixed voltage to frequency input. Okay, so we can say the V by F, variable frequency, variable voltage, correct? Output with appropriate form in the frequency, amplitude, number of phase that optimally suited the load requirement. Okay, so normally we can use in the induction motor, that is a V by F. So there is a voltage to frequency ratio, correct? So we have to maintain the voltage to frequency ratio, and then we can control the speed of the motor, correct? So nowadays, around 90% industry use V by F method to control the speed of your induction motor, correct? So power processing units, converter, basically 4 types. So that is a control rectifier. So we can say AC to DC converter. Okay, so we have AC supply, and we have to convert into DC supply. Okay, so that is your AC to DC converter. You already studied in the first semester as well as in the BTech, correct? DC chopper to DC. Suppose you have a DC supply, again you have to convert into DC supply, correct? So we can say the regulated DC supply. So that is a DC choppers. AC voltage controller, also we can say the cyclo converter. Okay, AC voltage controller. So we have a input is AC. Again we have to convert into AC. So we can say we can control in the amplitude of the AC voltage. So that is your also cyclo converter. Okay. And finally, fourth one, there is an inverter. Again, we have to convert DC supply into AC supply. Okay, so we have a 4 type of power processing unit. Depend on the your load, depend on your motor, we have to convert the power. Okay. Then second element, there is a controller. There is a most important part. Okay, governing the load and motor characteristic and their interaction. Okay, so we have to design the controller depend on the role load and motor characteristic. We have to design the controller. Okay, to match the load and motor through the power converter. So how we can design the converter? By using the power electronics converter. Okay. So suppose we can say this is your controller and this is your maybe the FPGA. We consider this is a FPGA, correct? Field programmable gate array. So there is a input, feedback, and other parameter. Okay, maybe you can sense any other parameter, maybe the flux, yeah, maybe the torque, any other parameter, and that parameter is an input. So we can say these all are input and these all are output. Okay, and output may be the multiple output. Okay, so depend on the system. Okay, so this is nothing but your controller part. Okay, so you can see first one is a power source, second one is a power processing unit, there is a power converter, and third one is a controller. So whenever we can say controller, so you can see there is a 3 inputs, input, feedback, and others parameter, correct? And one output, that is a maybe the speed, torque, yeah, depend on your system requirement. So controller input, there is a torque, flux, speed, or position command. Okay, maybe we can give controller input, that is a torque. Suppose you want to control the torque. Suppose you want to control the flux. Suppose you want to control the speed, and suppose you want to control the position. Okay, so these 4 parameters generally input of the controller. Okay, measure the torque, obvious. Suppose you want to control the torque, then you have to measure the torque, flux, speed, and rotor position, correct? So that is your feedback. Okay, limiting value of the torque, yes, we have to put the limit, so we have to give the some saturation point. Okay, so maybe this is your torque and this is your time in second, and this is your torque Newton into meter. So we have to give the some limitation, correct? It is not up to unlimited, correct? So we have to give the limitation, correct? Limit of the value of the torque, correct? So limiting the value of the torque, current, and acceleration, correct? Because torque current is directly proportional, torque and current is directly proportional, and whenever we can say torque and current is directly proportional, then we of course that acceleration is directly proportional. Okay, temperature feedback and instantaneous current or voltage in the motor or converter. Also we can give the temperature feedback. Suppose you want to measure the temperature of the motor, correct? The constant speed and position controller. Okay, so these are the input parameter for the controller. Okay, so depend on your requirement, you can control your input parameter. Okay, so what about the output? Okay, so output is control signal for the voltage magnitude. We can say the VC, there is a control voltage magnitude. Control signal for determine the frequency, there is a FC. So C stand on controller, okay, and F stand for frequency. Same here, C stand for controller and V stand for voltage. Control signal for the base and gate of the converter. So we have a power electronic switch. We can say there is a semiconductor switch. So we have to operate this switch, correct? So we have to give the gate pulses. Okay. So we have to control the gate signal, correct? So that is we can say the base or gate of the converter. And final word, protection and other monitoring function. So we have to also protect our devices from the high voltage overcurrent. So we have to provide the different type of protection system for our controller. Okay, so these are the output of the controller. So next part, there is a controller realization. Okay, so there is an analog or integrated circuit. Okay, maybe that is an analog type, otherwise maybe the integrated circuit. Then microprocessor, single chip microcontroller, DSP, and VLSI. Okay, any type of controller you can use. As I said, maybe we can use the FPGA. Okay, So depend on your requirement, you can use, because this microprocessor single chip microcontroller, every parameter that depend on the clock frequency. Okay, so suppose your clock frequency is very high, okay, and frequency that is directly proportional to the time. Okay, done. So your frequency is very high, that is a very good, so it will take the less time, correct, to operate your operation. And last one, complex control algorithm can be implemented, correct? So suppose your clock frequency is very high, so you can easily operate your complex algorithm. So you can get the output is very quickly, okay? So these are the major function we have to consider while design the any drives control algorithm, okay? Yes, now we can say the mechanical load. While we can say the mechanical load, then we have to consider the speed torque characteristic. Okay. So throughout the semester, we are discussing the only the speed torque characteristics of the different drives. Okay, maybe the AC drives, maybe the DC drive, maybe the synchronous motor. Okay. So always we can say speed versus torque. Always, correct? Because now subject is a electric drives, correct? So we have to control the speed and torque. While we can say the controlling of the speed and torque, then we have to plot this characteristic on the XY plane, correct? We can say the 2D plane. So you can see on slide number 12, so on the y-axis that is a speed, maybe we can say the RPM, and on the x-axis that is a torque, and maybe we can say Newton into meter, okay? So you can see we have a 3 graph. So this is the first graph, we can say graph number 1. This is your graph number 2, and this is your graph number 3. Okay, so we can say we have a 3 graph on the speed torque characteristic. Okay, so this is, you can see the parabolic graph number 1. So t is directly proportional to the n square, where n is indicate the speed. Okay, so this n is nothing but your speed in rps, okay, radian per second. Okay, and this straight line, we can say straight line, that is the torque is directly proportional to the n. Okay, and this inverse parabolic, that is a green line, there is a torque is indirectly proportional to the 1 by n. Okay, so inverse of the speed we can say, correct? And this red line, it is a torque is constant at any speed. Okay, so this type of characteristic is most important to analysis the any kind of drives. Okay, so we can say torque is directly proportional to the n square, torque is directly proportional to n, torque is directly proportional to the inverse of the speed, and torque is constant. Okay, so this characteristic is most important. Okay, where n equal to speed in rps, radian per second, and always capital A n, that is a speed in rpm. Okay, so student, this must be remembered by you. Capital N and small n. Small n indicate the speed in radian per second. Okay, and capital N, that is a rpm, radian per minute. Okay, so small n, that is a radian per second, and capital N, that is a rpm. Okay, so let's see the equation. Okay, so this is your load torque equation. So TL, that is a load torque, is equal to T naught. Okay, so at a zero speed torque plus CTR bracket N by NR power K. So TL, that is a load torque of your motor. T naught, that is a load torque at zero speed. Okay, and C, that is a constant, and this constant depend on the material property of your motor. TR, that is a load torque at the rated speed. Okay, so TR, that is a load torque at the rated speed. Okay, and small n, that is a operating speed. Okay, and K, that is a exponential coefficient. Okay, so we have this mechanical characteristic equation of your drive system. Okay, so please remember this equation number 1. there is a TL is equal to T naught plus CTR into N upon NR power K, and K, that is your exponential coefficient. Okay, so this is a mechanical load equation. We can say the equation for the mechanical load. Okay, is there any confusion, student? Any doubts in this slide? Yes. Any confusion? Madhusundan, any confusion?
No, sir.
Okay. Okay, good. So this is the slide number 13. There is a comparison of the mechanical load with the different condition. Okay. So first column you can see torque is inversely proportional to the speed. Okay. So here is a horsepower is constant. Horsepower means that is your power. Okay. So power is a constant. Okay. So we can say on the y-axis there is a speed, on the x-axis there is a torque, speed. Okay. On the y-axis there is a torque, on the x-axis there is a speed. Okay. So this is the characteristic for the torque is inversely proportional to the speed. And where we can use this type of characteristic, so what are the application? So we can say winders, facing length, rotatory cutting machine. So these are the few examples where we can use this type of application and this type of characteristic. Okay. Second one, there is a torque is constant. Your torque is constant, then obvious your horsepower is constant to the speed, correct? So we can say torque is constant, correct? So on the y-axis there is a torque, here is also torque, on the x-axis there is a speed. So torque is constant, so you can see your horsepower is linearly increase, okay? And where we can use this characteristic, hoisting gear, first application belt conveyor system, process machine involving the forming, okay, rolling mills and planers. So these are the few applications where we can use this torque is constant, okay, and whenever we can see torque is constant, then obvious your horsepower is directly proportional to the speed, okay. Third application, there is a torque is directly proportional to the speed, okay. And when we can say the torque is directly proportional to the speed, then your horsepower is directly proportional to the square of the speed, correct? Because power is nothing but your torque into speed, torque into speed, okay. So torque is directly proportional to the speed, so we can say power is n square, okay. So you can see horsepower is a n square, okay. And so on the y-axis there is a torque, on the x-axis there is a speed. So we can say horsepower is parabolic increase and torque is constant. And where we can use this type of characteristic, cylinder width, viscous friction, AD current breaker. Okay, so generally we use this type of application in the AD current breaker. Okay, then and last one, torque is directly proportional to the square of the speed. Okay, so whenever we can say square of the speed, then ultimately your power is a cube, correct? Again, this is the same formula we have to apply. So you can see on the y-axis there is a torque, on the x-axis there is a speed. So this is again is a parabolic curve. Okay, an application that is a torque is directly proportional to speed, that is a pump, fan and centrifuge. So these are the application of the mechanical load where we can use different type of characteristic. First one, there is a torque is inversely proportional to the speed. So this is your first one. Second one, torque is directly constant. Third one, torque is directly proportional to the speed. And fourth one, torque is directly proportional to the square of the speed. Yes, any confusion, student? Yes, Alok Yadav, any confusion in this slide? Yes, Alok, any confusion?
No, sir.
Okay, good. I think in the first semester we already discussed the active load torque and passive load torque. I think so. Again, I am repeating this thing. Okay. So active load torque and another one is a passive load torque. Okay. So active load torque means always effect on the motor shaft, even when the system is in the static state. Okay, so this is your active uh, uh, load. Okay, we can say always effect on the motor shaft. And second part, even when the system is static state. Okay, so that is the active source. Okay, active source, otherwise we can say the active load. Direction remain unchanged. So whenever we can say the active load, then direction is remain the same, maybe the clockwise, yeah, maybe the anti-clockwise. It will not change. So what are the example of the active load torque? So we can say example, potential energy load, load caused by the compressive forces and elastic force. So these are the few example of the active load torque. Okay. Then, and what about the passive load torque? So counteract the movement of the system. So it will change the direction. Then we can say it is a passive load. Okay. So we can say in an active load torque, it will not change the direction. But in the passive load torque, it will change the direction. So you can see reverse direction of the rotating speed. Okay. Then we can say it is your passive load torque. And what are the example? Friction load, load of the cutting machines. Okay. So these are the few example of the active load, active load torque and the passive load torque. Okay. Yeah. So till now we discussed the concept and elements of the electric drives. Okay. So any confusion still now? Then we can discuss the next topic, that is a speed torque characteristic of the electric vehicle. Not electric vehicle, electric drives. So there is a speed torque characteristic of the electric drives. So till now, any confusion, any query? Yes, student. Any confusion? Yes, Isa Tiwari. Any confusion?
No, sir.
Okay, good. So all are there, correct? Nobody is sleeping. Yeah, you are sleeping.
No, sir, we are not
No,
sleeping.
sir.
No sleeping, correct? Okay, good. Good. So now next topic, there is a torque speed characteristic curve. Okay, otherwise we can see the torque speed characteristic of the electric drives. Okay, and why we have to discuss this torque speed characteristic? Because we have to design the our drive system, correct? Maybe the AC drive, yeah, maybe the DC drives. Okay. So let's first discuss with the definition. Load, that is a torque speed characteristic. TSC stand on torque speed characteristic, the relationship between the torque and speed of the load. Okay, so we can see we have a torque speed characteristic on this speed and this is a torque. Okay, so we have to plot the characteristic, we have to plot the relation between the torque and speed on the XY graph. Okay, so that is a nothing but the definition of the torque speed characteristic. Okay, motor torque speed characteristic, a relationship between the torque and the speed of the motor. Whenever we can see the load torque characteristic, then there is a relation between the torque and speed of the load. When we can say the motor torque speed characteristic, there is a relation between the torque and the speed of the motor. Correct? It means suppose you discuss with the load and suppose you discuss with the motor, with respect to that parameter, we have to analysis our torque speed characteristic. Okay. The natural torque speed characteristic, the motor torque speed curve when it working in the nominal rated condition. Okay, so that is a normal condition. It is operate in the steady state condition. There is a normal operation of the natural condition of the torque speed characteristic. Okay, and when we can say controllable. Okay, so this is your controllable. Controllable torque speed characteristic achieved by adjusting one or several electrical input parameter. Okay, it means we already know, suppose you want to control the speed, suppose you want to control the torque, then torque is directly proportional to the current and speed is directly proportional to the voltage. So you can control the any one of these parameter, then you can control the torque speed characteristic of the motor. Okay, so this is achieved by adjusting the one or several electrical input parameter. Okay, and what are the input parameter? There is a voltage and current. So these are the two input parameters which we have to control. Okay, each motor has family of the curve. Okay, so we have a series motor, there is a DC series motor, shunt motor. We already discussed the characteristic of the series, shunt and compound motor, correct, in the first semester. So these are the speed torque characteristics of the our electric drives. Okay, so there is a depend on the load, depend on the motor, depend on the natural response, and depend on the control. Okay, done. So we can go ahead with the little bit modeling part, because subject name is a modeling and analysis, modeling and control of the electrical drives. Okay, so till now we discussed the how we can control the electric drives. Okay, so now slowly we are going with the modeling part. Okay, how we can model the torque speed characteristic. Okay, correct. So equation is simple. There is a beta is equal to del T stand on the torque divided by del omega. Okay, so beta, that is, we can say the hardness factor of the torque speed characteristic. Okay, so equivalent we can say the del T by del omega, and del, that is a variation of the torque. Okay, and del W, there is a variation of the speed. Suppose T equal to 0 second, your speed is 0 rpm, then we increase the speed at t equal to 5 second, correct? So we can say the delta variation is a 5 second, our speed variation is a 500 rpm, correct? So that is a delta variation. Okay, range of the speed control, that is a D, capital D, we can define maximum speed upon minimum speed. Okay, so we can say the maximum speed, that is a 1000 rpm, divided by minimum speed, maybe that is your 100 rpm. Okay, so both are the rpm. Okay, and that is nothing but your capital D, and capital D is nothing but the range of the speed, correct? Okay, and smoothness of the speed control. Okay, smoothness of the smoothness of the speed control, that represent by the gamma. Okay, and what gamma say? Gamma say that is omega I plus 1 divided by omega I. And what is the meaning of I? I indicate the time instant. Time instant. Okay, suppose I equal to 5 second, your speed is a 1000 rpm, correct? Suppose I equal to 10 second, your speed is a 1500 rpm. Okay, so that I indicate the time interval. Okay, so we can say I indicate the time interval. Okay, and omega indicate that is your speed. Okay, in radian per second, correct? So these are the simple modeling of the torque speed characteristic. Okay, so you can see here is a speed. So this is your speed on the y-axis, and here is your torque of the motor on x-axis. Okay, and you can see the various condition they are taking. So this is a condition 1, condition 2, and condition 3. Okay, so we can say suppose we have any type of motor, then we have to design the torque speed characteristic, and that is your first task. Okay, then yes, yes. So this slide, that is again is a mechanical load torque. We already discussed this slide. Okay, so this is your most important torque equation, and there is a relation between the load torque and the initially torque, as well as the your rated speed. Okay, so again this is a load torque equal to initial torque plus C, there is your constant, and again that is depend on your motor parameter, motor material parameter, TR, that is a rated torque, N upon NR into power K, and K, that is your exponential coefficient. Okay. Yes, there is another way to express the load torque, because friction is present in the motor, because there is a bearing because we have to rotate our shaft. Whenever we can say we have to rotate our shaft, so there is a bearing part, correct? So finally we can say our load torque expression in the terms of the bearing, in the terms of the friction. So we can say TL, there is a load torque, is equal to TR, there is a constant torque, plus B omega. This equation we already studied in the first semester, okay? And also we implemented in the MATLAB Simulink, correct? All of you implemented this equation in the MATLAB Simulink, correct? So TL equal to TR plus B omega plus C omega square, okay? Where TR, that is a constant torque, Newton into meter, viscous friction torque, and CW, C omega square, that is your aerodynamics drag torque, okay? So these are the equation number 2, we can say, and these are the equation number 1, we can say, okay? So these are the most important equation, that is equation number 1 and equation number 2, okay? And motor torque speed characteristic, so we already studied different type of motor characteristic in the first semester. In the second unit, there is a DC motor operation, okay? So we can say the modeling of the DC motor, okay? So there is a series DC machine, separately excited DC machine, shunt machine, compound machine, and induction AC machine. So you can see that we compare all the type of motor characteristic in the single plot, correct? Okay, so I'm not going to repeat same characteristic again because we already discussed this characteristic in the first semester, correct? So this is the same characteristic repeat in this second semester because this is a fundamental concept of your modeling and control of the elliptical traverse. Suppose you don't know about the characteristic, this speed and torque characteristic, then you will not able to you will not able to design your drive system, correct? So that's why I am focusing, that's why I am strong indicate the torque speed characteristic of the different type of motor, okay? Done. So somewhere is a joint characteristic, okay? So somewhere maybe the intersection of the one characteristic to another characteristic, okay? Then we can say it is a joint characteristic, okay? So how we can define? So load have a wide range of the speed torque characteristic, okay? Your load may be the wide range, okay? That may be the possible the joint characteristic. Second case, electric motor exhibit variety of the speed torque characteristic curve. Your speed torque is a various operation, okay? There maybe we can see the dynamic operation, okay? Then third one is the equilibrium condition, okay? Third one is the equilibrium point, that is an intersection. Suppose this is your speed torque characteristic, this is a speed and this is a torque. So maybe we can say this is a one torque, one graph, this is a second graph, and maybe we can say this is your third graph, correct? So this is your intersection point. So we can say this is an intersection point, correct? So we can say this is an intersection point. So we can say maybe the name is A. So this intersection point, it is called the equilibrium point. The equilibrium point, how we can define? The intersection of the two curves, okay? So we can say intersection of the two curves because two curves is minimum to intersection of the any characteristic, any line, correct? So we can say now we have three lines, line number 1, line number 2, and line number 3, and all lines are intersection with the each another, correct? So this is nothing but your equilibrium point, okay? And last one, the speed of the system is not determined by the motor only, okay? The speed of the system, this is most important. The speed of the system is not determined by the motor only. Then how we can determine? But it is also heavily depend on the mechanical load characteristic. That's why we have to define the mechanical load characteristic also, correct? So we cannot say your speed of the system is determined by the speed only, by motor only. No, we have to also consider the load characteristic, okay? So these are the important point for the joint characteristic of the speed torque, okay? So you can see this is a example of the joint TSC, that is a torque speed characteristic. So this is a fan characteristic, and this is a hoist operation. Hoist is a constant operation, correct? So torque is a constant in the case of hoist, and fan, that is a torque is directly proportional to the square of the speed, correct? So that is a, you can see the characteristic of the fan and characteristic of hoist, and both are equilibrium point where to F1, F2, and F3. Okay, there is a fan, H1, H2, and H3. That is your hoist. Okay, so these are the characteristics for the joint TSC. So these are the last topic. Then I will stop the class. So there is a motion dynamics. Okay, so how we can define the motion dynamics? Okay, so we can say the linear motion, and another one is a rotational motion. Okay, so you can see this is a linear motion, and another one is a rotational motion. How we can define the linear motion? Suppose you want to define the position, then we can indicate by x, and for the rotation there is a theta. Same, suppose you want to define the velocity, then we can define by small v, but in the case of the rotation, that is your omega, that is the angular velocity, correct? Same, there is acceleration, we can define capital small a for the linear motion, and here is alpha, correct? So you can see the motion equation is there, mass is there. For the mass, there is a m for the linear motion, but in the rotation there is a I, there is a moment of inertia, we can say I or j, correct? We can say j is also moment of inertia. Newton's second law, all of you know, there is F equal to ma. Okay, so where m we can indicate by I या j, and a is indicated by alpha. So that is your Newton's second law. Momentum P equal to mv. So here is we same, we have to L equal to I into omega, otherwise j into omega. Work done, that is your F into d. So F is a force, and F is a force, and d is a distance, correct, for the linear motion. But in the work for the rotational motion, there is a torque into theta, correct? Kinetic energy 1 by 2 mv square, and here is a rotational 1 by 2 j omega square. And finally, power, we can say force into velocity, but here is a torque into omega, there is a power. So this formula is most important formula. Okay, so these are the most important formulas. Okay, so you should remember this formula. As a power electronics and drives engineers, you should remember this formula, because this is a linear motion as well as the rotational motion. Okay. Yes. So this is a simple example of the linear and the rotational motion. Okay, so you can see here is a two part, we can say. So this is a mass. So this is a mass force. Okay, so we can apply from the left hand side to force, and we can also apply from the right hand side to force. That is a FL and FM. FM indicate the mass force, and FL indicate the load force. And this is a velocity. So we have to move the mass in the right hand side. Okay, from left hand side to right hand side. Okay, whenever we move the mass from the left hand side to right hand side, there is always the opposite side of the force, correct? And that opposite side of the force, we can say maybe the air force, yeah, maybe the any external force, correct? So in this example, we consider there is a FM, there is a motor force, and this is a FL, there is a load force, that is a oppose your motor force, correct? So we can say summation of force, that is a d mv divided by dt. With respect to time, your mass and velocity will change, correct? So finally, we can say summation of force, that is a Fm minus Fl, okay, Fm minus Fl is equal to dmv upon dt, and dt indicate your time variation, correct? Same thing we can apply for your rotational motion, correct? So m is indicated by j. So just replicate by linear motion by a rotational motor, okay? And this is load torque, that is moving in the anti-clockwise direction. Motor torque, that is rotating in the clockwise direction, and this is your speed, that is rotation in the same like motor torque, okay? And then same again, we can write the equation, that is a summation of torque is equal to d by dt into j omega. Okay, so we have to just replace that m with the j. Here is also we replace m with the j, correct? And this is a v is a velocity, but here is a v is your omega. Okay, so finally you will get the torque, that is a Tm minus TL, because this is a total load torque, and total torque you can see Tm minus TL, correct? So that is a d j omega by dt. Okay, done. So this is a simple. So this is, you can see, this is a rotational. Okay, this is your radius, and this is omega. Okay, anti-clockwise direction, and this is, you can see, the linear force. This is again is radian, and this is your torque. Okay, so torque is nothing but radius into force, and velocity is nothing but your radius into omega. Okay, so this is a simple 10th class standard concept. Okay, suppose we have any circle and we have a radius, then what are the rotational speed, correct? So radius is already defined, rotation speed is defined, so we can easily find out the velocity. Okay, this is simple concept, that is a standard of the 10th. Okay, so this is the last slide, that is a moment of the inertia. Okay, so we already discussed the moment of inertia in the first semester. Okay, so inertia is the resistance of the object to be accelerated or the deaccelerated. Okay, so this is a moment of inertia. Every body there is a mass, correct? So maybe my weight is maybe the 60 kg. So another student weight is a 70 kg, 60 kg, 50 kg. So there is an inertia, correct? So every system have inertia, correct? So we can say the body mass. Okay. So moment of inertia is the name given to the rotational inertia, correct? Rotational analog of the mass of the linear motion, correct? Inertia is nothing but your mass, and that is indicated by J, that is a kilogram into meter square, correct? So that is a linear motion, we can say F equal to ma, that is a Newton's second law. Linear motion, that is a Ke 1 by 2 mv square, that is a kinetic energy, correct? And there is a momentum, there is a P equal to m into v, correct? And here is a linear motion, that is a 1 by 2 mv square. So these are the simple motion dynamics equation. Also we can see the moment of inertia, simple 1 by 2 j omega square, there is an angular moment of inertia, correct? Okay. Yeah, so these are the some example, not example, we can see the few formula for the, suppose your moment of inertia for the center of gravity, solid cylinder, hollow cylinder, then how we can define the moment of inertia, correct? This is not important, but this is just for your information, correct? And mass of the moment, transform or rotating motion, okay? And J, that is a kilogram into meter square, M, that is in kg, R, that is in meter, and V, velocity, obvious, meter per second, and omega, that is a speed, radian per second, okay? So these are the few examples. Suppose you have a cylinder type, the rotor, that is a cylinder type rotor, maybe the hollow type cylinder, any type of rotor category, then we can easily find out the moment of inertia, okay? And there is a state forward formula. Yes. So key point from the today's class, we discussed these are not the key point. So I will change this slide. So we discussed the fundamental of the block diagram of the electric drives. Then we discussed the different type of elements of electrical drives, and then we discussed the torque speed characteristic, and final topic we discussed the motion dynamics of the electric drives. Any confusion, any query, student, from today's class? Yes, student, any query? Okay, no query. That is a good, because this today's class, that is a like revision of your previous class, okay? And there is a fundamental of the electrical drives, okay? From the next class, we will start the 4 coordinate operation of the electrical drives, okay? So we will study how we can operate our motor in the 4 quadrant. So forward motoring, reverse motoring, forward braking, and reverse braking operation, okay? So there is another important topic for the electric drives. Okay, so if you don't have any query, then we can stop our class. Okay, done. Yeah. So maybe you can leave now. It is
Okay, sir. Good night, sir.
good night. Have a nice day.
Okay, take care, sir.